Okay, so we will actually go ahead with the calculations which we were actually trying to do last time. So I thought I have told last was there are two metrics which have to be used for performance analysis. One of them was throughput, and other one was turnaround time. So the way they are defined, that throughput is nothing but average number of packets which are being pushed out per unit time. That is how throughput is taken. It has nothing to do with the input. Of course, if you keep on changing your input rate, throughput will change, and throughput ultimately should saturate. Okay, throughput ultimately should saturate. Turnaround time will be your average time interval between instants when packet arrives at input of network and when packet leaves at the output of network. Okay. And of course, the maximum throughput will be existing when there are no conflicts. So, for example, at each input you have packets in such a way that there are no conflicts, and all of them can be pushed without any contention to the outgoing port. So, that will be the case for maximum throughput, and minimum turnaround time also will happen when there are no conflicts, because you will not be storing anything in the buffer, just pass through. Okay. So, usually then we use the normalized version of these. So whatever the maximum throughput possible, you can normalize with that. This will ensure your normalized throughput is always less than 1. Okay, this for comparison sake, it is independent of sizes now. So that is a normalized value. Similarly, for turnaround time also. So what is the basic unit of time counting? You are essentially looking at that. So you will divide it by minimum turnaround time. Okay. So these are the two normalized versions which actually have to be used. So first of all, we will actually estimate the same thing for unbuffered delta, not the buffered one, but unbuffered one, which we had done earlier. Okay. So this one is pretty simple. So for a 2 raised power n by 2 raised power n unbuffered delta, you can assume Pk will be the probability that so remember the K subscript. So, for different edges there will be different probabilities. So, I can actually iteratively compute, if I know the input probability, I can compute what will be the output probability, and that will give me a throughput. That is basically the idea here. Okay. And from here you can define Pn in the similar fashion. This is probability that the packet arrive at output link. All n stages have been finished. There are total n minus 1, 0 I am counting 0, 1, 2, 3, n minus 1 are stages. The moment I talk about Pn, that is output link, okay, because there is nothing like a Sn stage is not there, S0 to Sn minus 1 are there. So, this will be your technically your throughput actually. Now, there are certain assumptions which have to be there. So, at every intermediate switch, in general there can be many inputs, and as we had done earlier, each one of them is going to connect to a set of inputs. So, each one of these inputs will be connecting to set of inputs of the network. So, in earlier case it was only two set Ix and Iy I was talking about, they were always disjoint. Here also all the sets which you are going to form will be disjoint. Once they are disjoint, since all arrivals at the network are independent, and they are kind of independent identical processes actually, arrival process. So, that independence also holds true here. In fact, it holds true at every intermediate switch. Okay. So, this actually means I can assume that Pk is going to be same for all links, all input links to stage k. So, not only this switch, in that stage whatever number of switches are there, all inputs in that stage they will be all independent actually. So, there is no correlation between them, and this actually you can keep on extending. It means this Pn will be same for all output links also, that independence will still be maintained. Not for output side, but yeah.
Pk is same for all switches at stage k. Pk is the same for all.
Pk is going to be same for all switches in stage k, right. Each one is an independent set actually, and each one of them will be now connecting to 2 raised power k inputs. So, since the number of inputs are actually being same to which it can reach, and each set is different, okay, within a switch each set will be different. So, this will be showing independence. This is actually true for everybody. So, they are going to be same, they are independent within a switch. If you take two different switches, then they are not independent, because they might be coming from the same input. But since every packet is also coming independently, it is okay, because independence comes because of the fact when a packet comes with the equal probability, it is choosing an output destination. There is no bias. With 1 by n probability, 1 by 2 raised power n in this case, it is going to choose any one of the outgoing links, and each packet in all inputs are going to do the same thing. So, statistically, yeah, every input port is technically same. You just find out probability at one place, use it at everywhere, unless you have asymmetric situation. It is a symmetric or uniform traffic conditions actually here. And important thing is that it is independent of what kind of delta network you are taking, whether it is a shuffle net based or it is inverse bench or whatever you can design, or it is a omega network or whatever it is. So far it is a delta network, the situation is going to be true. In fact, it is true for any Banyan network, not only this. Only in the case of Banyan network is that tag, the address tag will not be uniform for a given output. Address tag has to be different at different inputs for same output actually, that is the only variation. But so far that condition, there is exactly one path from any input to any output is maintained, and no input links and no output links in the intermediate stages are left open. This is going to be true. Okay. Technically it is a demultiplexer tree which you are building all the time, and of course this is now throughput. I can write a simple statement from here. Now paper actually gives slightly different variation here. I also could not figure out why it is being given that way, but what it is saying is, in the whole switching network of k stages, when the packet enters and packet goes out, that is a period which is min d. So one lot of packet comes in, it takes min d to go out, and once the min d is over, then the next packet will come in. So there is one packet being injected at each input, or if p is the arrival rate or the probability of having a packet on this input side, the p fraction of packet on an average are being injected per min d slot. So min d is kind of a slot, but actually it is not required. In one slot, if I am moving from one stage to another stage, so I can use pipeline. When the packet moves here, the another packet from input can come in here. So technically my number of packets has to be this particular slot. That assumption has not been taken while computing the throughput performance. So throughput actually can be k times technically than what I am writing. Okay, if this pipelining is also assumed. So pipelining is not assumed in the paper. That is one thing which is done there. So throughput will be nothing but p raised power n, which is probability that you are going to have a packet at the output link, and total number of output links will be 2 raised power n, and these many packets will go per min d slot, but need not be per min d slot, it can be per min d divided by k. So k times higher actually it can be achieved. So that will be the throughput. I am just going to state whatever they have told. So this will be the throughput for all unbuffered delta networks. In fact, for that matter all Banyan networks. So far that condition is satisfied, that no input and output links in the intermediate stage are left open, and you have exactly one path from each input to each output. And this, we have to just estimate what is Pn. What Pn has to be done through a recursion. You cannot make a direct estimate once the P at the input link is given. So in this case, now every stage you are going to have a switch, remember, and you are connecting them like this, whatever way, I am not bothered currently, something must have been done. Now each of these switch can be of A by B size, general crossbar, or in this case it has been taken as B, symmetric case, it is not asymmetric case. You can solve for asymmetric case also, that is also fine, where A and B both are not equal. Now number of packets which are going to come are binomially distributed. They are B inputs as a single unit crossbar, remember, which is a simple switch. So for a crossbar of, actually you can do it for in general for A by B also. This paper does for B by B. So the packets which will arrive will be binomially distributed. So, there can be j packets which can be arriving, and this arrival can happen with the probability, here the probability is pk, remember, probability that a packet will come will be pk at an input port. So, this actually means BCJ, that is the probability that j packets will come, and probability that a packet, you take an output link. So, this probability is nothing but will be pk plus 1. Okay. So, probability you will have a packet on the outgoing link, that probability is there has to be at least one packet out of these which is selected here. This can happen for all outgoing links with equal probability. So, this can be estimated as probability a packet and this is under the condition that given that j packets arrive at inputs. So, this value will be nothing but, you will simply say that each packet, now this is a conditional probability, j packets have already arrived, I have to multiply by this is a conditional probability, remember. Okay. So, this probability is that out of these j packets which have arrived under that condition, none of them is being directed to an outgoing port, I can find out that probability, and each outgoing port is going to be selected with equal probability, actually the 1 by b. So, you will have 1 minus 1 over b, that is the selection probability. See, and 1 minus 1 over b, that you are not going to select an outgoing port, none of the j packets will be going to select an outgoing port is this, and 1 minus of this, at least 1 is going to select an outgoing port, 1 minus of that. So, that is a conditional probability that packet will be there given j packets. Okay. And then of course, you can find out what is pk plus 1 from here. So, from here pk plus 1 so j can go from 0 to b, and of course, this is a conditional probability 1 minus 1 over b j, and I just multiplied by whatever is the condition which was BCJ so this is absolute probability that there will be at least one packet at the outgoing port. I have just summed up with all possible j's. The condition thing I have removed technically. So, this actually can be solved, and this will turn out to be, so this whole thing now can be written as this one, actually I am taking out summation of one minus 1 over bj and pk I can combine actually. So, this term is a complete binomial, so it will become 1. This one is also, I can always write a raised power j and b raised power p plus q raised power b, that form I can use, again it is a complete binomial. Okay. And based on that I can get the solution. So, it is an iterative thing which we will get actually. So, it will be 1 minus So that will be the probability of pk plus 1 in terms of pk. This I think you can also figure out, was for input queues we have done similar thing when the packets were dropped, okay, except this pk was converted to something else there. And of course you can always take, for the maximum loading condition, p0 can be taken as 1, and from there I can find out what is the maximum possible throughput which you can have. So even a buffer delta will always have throughput which is lower than this. That is the maximum which you can get. This is not maximum, sorry, this is not maximum. So this throughput is p0 is at 1 you can compute, and maximum throughput is all outgoing packets will have a, without conflict this is a maximum throughput, you divide by this actually. So normalized throughput you will get is nothing but p of n, which you have to get from here, but this has to be solved through recursion. So p1 will be 1 minus 1 over b, because p0 is 1. So this is going to be smaller value actually, every time the value will keep on reducing, decaying actually. So every step you will do it after k stages, find out what is the value of pn, and that is your throughput. That is a normalized throughput, the whole pn. You are dividing by this value. Actual throughput which I defined was pn into 2 to the power n by, but maximum which you can achieve is when all outgoing ports will actually have one packet every min_d slot, and if you allow pipelining you multiply it by k.
Is k the number of slots in the minimum d?
Min_ds contains
K slot.
k sub slots. Each sub slot you go from one input stage, from the input of a stage to output of the stage, for every stage.
Sir, you have to sum up, I mean recursively means you assume pk plus 1 and then further you have to go, or just pk plus 1 will be.
You know how to get pk plus 1 from pk.
Yes, sir.
So if you know p0 is being 1 under maximum loading condition, what is p1 you can find out.
Yes, sir.
So p1 will be,
You need to sum up all these after this. No.
why you need to sum up? You are getting absolute value. Sum up is only when p0, p1, p2, p3 all values are there. You do not know their values, but you know their relations. So then use last one when you will say sum of all probabilities has to be equal to 1 is the last equation, which makes your number of equations become equal to number of variables to solve each one of them. Here you are getting the values actually directly. There is no Markov chain actually, it is not a Markov chain. You will put 1 over 1 minus b, this is the p1 with value b, p2 you will can find out now putting p1, find out p3, p4 so on iteratively, is a recursive relation which you can get at best.
So why are you using binomial expressions over here? I mean,
That is what I get.
there are n inputs. You can use exponential or even Poisson ratio for that.
I am not worried. I am not worried about the input statistics. Input statistics, the packet is always there. So in a input statistics cannot be exponential or Poisson. Remember, there is a reason for that. I am talking about a discrete event, discrete time system. These are slots. So packet can only start here, and it can be, it has to close by one slot. So only statistics which you can use is either a packet can be there or cannot be there. So this is nothing but P, you use the probability. So on an average how many packets per unit slot you will have, it is P. P is a probability then, and that is the arrival rate per line. So most of the discrete time systems, that's what you are going to use for packet switching systems. Packets are not coming at any arbitrary time interval. If that is permitted, then that's a different situation. In our case, it is not. It is a fixed length packets coming. One packet can come in one time slot. You cannot have two coming in actually. Those systems actually can be done, but usually the way we do it in that case is, if you have a switch for example and there is one outgoing link with buffer, and there are many inputs which are coming in, they are not time synchronized. All these packets which are coming will be put in one single queue. Now since they are not time synchronized, I cannot get, in this case technically what I am assuming, because all slots are synchronized, they are fixed length. In one time slot I can get either 0 packet, I can get 1, I can get 2, I can get 3, that is a binomial thing. But if I am not permitting synchronization and all packet are of fixed length, then packet can arrive at any point of time on time scale. They cannot, then all of them need not come simultaneously. It is not 0, 1, 2, 3 in a slot. So packets will come sometimes here, sometimes here, sometimes here. Then I talk about inter-arrival time, which is exponentially distributed, or alternatively a Poisson distribution, that how many number of packets will come in per unit time. Because these are all independent, because of that independence I can take that assumption. Not at a source. Source usually actually have a correlated what we call arrival process. But as you go into the core, when the packets will get dispersed and packets are coming from various different sources, then only Poisson statistics can be assumed.
Actually sir, had I made some assumption like number of packet tends to infinity and probability of each packet arriving is very close to 0, then I could have approximated it by Poisson distribution. In that case it would have turned out to a limiting case of binomial distribution.
Fine, but then what is happening is, you are assuming this time slot to be
Very small.
very small. That is what you are technically doing. So continuous time variable is nothing but a limiting case of this, when packet can arrive not at discrete intervals but at any time interval, at any time instant. Real life always works this way, it is not this. But if there are many incoming lines, you cannot control what is happening in the behind, you can always use it as a Poisson thing. So when you look at this kind of queuing system, okay, then you will say that the statistics, arrival statistics here is Poisson. But that does not matter, we will always be doing the Poisson, this thing, binomial only.
Poisson will not give the length of the packet, it will give the only.
Poisson will give only the number of packets which are going to come per unit time.
Per unit time.
The length of the packet will tell you what will be the departure process. If all packets are of fixed length, it is a deterministic departure process. So you know that what is going to be, it is a fixed length. If you know packets are only of length L and L1 and L2, they are only two deterministic departure times, either it will take time t1 or t2 with some statistical distribution. And if it is exponentially distributed, that is what we assume most of the time, then you will define this thing as 1 over mu will be the average processing time, or number of packets which can be processed per unit time will be mu, is the departure rate. But we are not looking at these cases here. Important thing is that we are going to use iterative thing to build up the outgoing probability. So you will be able to get Pn from here and hence for the throughput performance.
Sir, what is the intuitive explanation for in unbuffered case we are having throughput higher than in the buffered case? It is because in unbuffered
Buffered case you can see that every time the probability is going down. So I am actually assuming if there are j packets for example, I am taking these 4 ports, I get all 4 packets, all 4 wants to go to this outgoing port, only one of them will be going. So remember, when I am looking at the probability, I am actually telling even if one or more than one, if they are trying to go to an outgoing port, one will go. That is how I am estimating pk plus 1. So it means remaining are being dropped. while in case of a buffer delta case, this is not going to happen. And of course, we are using a buffer delta model, we are using back propagation of the signal. So that the input itself, at least we will get the what is the maximum throughput which can be achieved under maximal loading condition. In this case, you put maximal loading, the throughput is limited to Pn when P0 is going to be 1. So you will find this as a maximum throughput. Crossbar, I need not do this iterative calculation. Crossbar and this are only different in what? This is a calculation for a crossbar technically. Okay, B by B crossbar. But I am using recursive nature of that. So every time probability is falling down because of recursion. In case of a single crossbar, same thing will now become, your P1 is 1 minus whatever was P0, 2 raised power n, 2 raised power n. That will be your throughput performance. So P0 you can make it 1 if it is a full loading condition. So this is what will be your value. And of course, when n becomes very large, 2 raised power n becomes very large, this can be approximated as so P0 you can put to 1 minus e raised power minus 1, which is 0.632. So that is a maximum throughput which you can achieve with a crossbar, single crossbar. The whole switch is implemented using a single crossbar, or I am using it implementing by multiple crossbars now by creating delta network. Yeah, there is one single crossbar being used for the whole switch. So unbuffered delta, we know that how we will compute. For this one we know how we are going to compute, but this has to be done computationally. There is no closed form expression which can be plotted, but these are exact computational results which will be there.
So we have calculated two results. First is the unbuffered delta, the throughput is Pn.
Pn, normalized throughput will be Pn.
Yeah, divided by this maximum.
So similarly you can also normalize this also if you wish. You have technically normalized this when you say P1. So maximum is whatever is to the power n divided by min d. So that you have normalized. So P1 is your throughput, here is that's a Pn. So Pn certainly will be less than P1 or more.
So what we want to say, for all loop class 2 and delta network, the performance under those scenarios, performance is almost same.
In throughput performance will be same for all delta
All
networks.
delta network under those conditions, what is mentioned.
Under all blocking conditions, because there is no blocking technically. The switches are all symmetric in one single stage and all inputs are independent. If the independence is not there, then the performance will be different. Then you have to assign the input ports such a way that if there are two correlated inputs which are always going to pump the packets, make sure there's two correlated packets are always going at different switches in the different stages. They should not never come to the same stage, because they should not try to pump the packet simultaneously.
Second case we have calculated for?
Is a crossbar implementation.
No, the pk plus 1 we calculated.
This one.
This one is a crossbar. Single.
This is a single crossbar implementation of the 2 raised power n by 2 raised power n switch.
First previous one, pk plus 1.
That one I am using B by B switches to create 2 raised power n by 2 raised power n switch.
But
Delta.
so there is one doubt in this. A cross B, if we have, the throughput will be same, or for asymmetry?
The formula will become different, that's the only thing. Formula will be different in that case. You can compute, not an issue. You can compute for A by B. I should have done that because that is done in the earlier paper. I had actually have not done the analysis at that time because that was anyway required to be done here. But this paper only talks about the symmetric case. So for A by B it will be. So what's the probability? If you have a probability Pk known here, what's the probability that you will get at least one packet on this side? So each packet is being uniformly distributed over this thing. Okay. So number of packets which will be j, you can actually compute that. So okay, so pk by b, that's a packet is going to come to certain outgoing port. Okay, none of the packets are going to come to this outgoing port. 1 minus of this and all possible j scenarios actually. No, all this will be a, sorry, this will be a, all inputs. This one only tells that at this particular input I will have a packet with probability pk. With pk by b, this packet will be directed to this outgoing port. 1 minus of that, this packet which is going to come here will not be directed here. This should be true for all a, so I have to multiply it by a. It's not ba, bb here. That's the only difference which will come. And 1 minus of this, there will be at least one packet going to which is going to come out here. So your pk1, this will be equal to pk plus 1. So this recursive relation will change in this case.
So this recursive relation is for buffered network, sir?
No, unbuffered. There is no buffering here. Buffer delta is tricky to handle.
Then when I normalize that relation by p, I get the second expression 2 power n by mu.
Remember in the switch, total outgoing ports are 2 raised power n. Best case can be when every min-d slot one packet is going out. If one packet is going out every min-d slot, so throughput performance is 2 raised power n packets per min-d slot. That's the maximum throughput. So whatever throughput actually you compute, divide by this to normalize it. So that's what is being done. So you divide this by 2 raised power n by min-d, you will get this. So you will get pk. Pn will be the throughput. I have written somewhere. Yeah. So this will be Pn will be the normalized throughput. So I just find out what is the value probability at the outgoing port. Per port throughput I am estimating technically. Okay. Per port maximum throughput is 1. So I am just estimating that Pn.
So in the previous discussion, sir, we took 1 minus 1 by b, therefore of j. So that is j is the count of number of packets which are coming in at the input.
I could have directly calculated also, but I did it explicitly for j packets come with conditioned on j.
So since a is the number of input lines, shouldn't it be apk, sir? And the it should be raised to apk, because apk will give the number of packets.
Number of I am not clear.
Arrival rate is pk, sir.
You are telling this has to be pk by b raised power apk.
Yes, at least it is raised to that exponential where it is number of packets which are there. Because
Okay, let me compute with j packets if you want the other way around. This was a direct calculation. Suppose j packets are going to come here. What's the probability for that? ACJ. When j packets have arrived, what's the probability that at least one packet will be coming to an outgoing port? So this is a condition, so that probability is 1 minus 1 over b, j total j packets, sum it over j. J can go from 0 to a, remember. Solve it, you will get exactly same thing. That pk will not come in the exponent. Just a way to understand actually. So both are fine, no questions so far. So next is, now we have to go to the actual analysis of buffer delta system. Now buffer delta system, I have to now look into what we call state transitions of a switch. So before I move on to that particular thing, I have to define the switch state. Now remember, there are buffers which are involved here. So there are all possible combinations are there. So we will define 14 states of the switches here, and that I will use in a building up the recursive relation. Again, this is done through a recursive relation which is computationally computed. Okay, there is no simulation, it's a actual calculation which has to be done. So, it is a computational procedure. So, there is no closed form expression as such, but computationally you will get the exact values. So, the model goes like this. Most of the states I am looking into 2 by 2 thing. So, one state is when the buffer on the outgoing side, which is nothing but the input buffer of the next stage, okay, that is free and this is free, that is one particular possible state. So, this is known as state 1. Yeah. So, I am keeping all the inputs free and then trying to put packets on the output side buffer. So, one possible states, I am just enumerating the states now, when you will have only one packet. Now, you can say this packet can be here or this packet can be here, but both are equivalent states. So, both are going to be, all equivalent states are merged together, the way we had done earlier. Okay. So, equivalence is I can rotate, swap, do whatever it is, but input and output cannot be swapped, the way we did in the earlier case, okay, in case of that white sense non-blocking system. So, this is a state 2. Okay. Third one will be now when I will have 2 packets which will be there. This is state 3. Whenever the packets are there at the input buffer, they will be directed to some outgoing port. There was no direction of the packet was shown because there were no packets at the input buffer. So, in this case, this is what will be the direction. Now, remember, even if this direction is not this, I put it like this way, this is equivalent to the earlier states because I can swap these 2 ports. So, it does not matter. Okay. So, I will represent this thing by this, because these numbers will be used, remember, these state numbers. I will be mentioning in the subscripts later on for the, in that computational model. Then you will have a state. So, I am looking at one input and then one in output, 2 output kind of combinations, all possibilities. So, one is this is state 5. Now, this input can be directed to this one, that is one possibility. This can be directed to a free port, that is a 6th state. Now, whether you direct to top or bottom, it is all the same. There is only one input. Basically, this cannot go because this is already filled up. So, this is a state 7. Then you have all cases when one input was there in the switch are taken care of, now 2 inputs which are there. So, if there are free ports, one possibility is both of them will conflict, that is a state 8. They do not conflict, that is the state 9. So, whether it is a bar state or cross state does not matter, there is no conflict. When 2 inputs are there, both will be state 9.
State 7 will be conflicting? State 7 will be conflicting?
Conflict can only happen if you have more than one input, but it cannot go on to the outgoing buffer because the next buffer is occupied for some reason. So, no outputs I have taken care of. 1, this could be one case. This could be one case. and then you will have state number 13 and state number 14. Cross and bar states in this case are exactly same, they will all merge into state 13. Okay. So whether the conflict happens because both want to go up or both want to go down, both are same states here. There are total 14 states which we have to define for a switch. So all switches will always be existing in one of these 14 states in a buffer delta system. Okay, so now here I actually close the today's lecture, and we will start now looking into probabilities and steps which are required for doing computational stuff for buffer delta. So that we will do on Thursday. You have to actually refer to the paper because I am trying to do it as slowly as possible, but still there will be confusions.